All right, welcome to 15.2 where we're going to talk about graphing log functions. Okay, you learned about log functions in 15.1. You learned that they are inverses of exponentials and how we were able to take an exponential and write it in its alternate log form and vice versa. But now we're going to talk about graphing and what the graph looks like and the transformations. Whoops, come on. All right, what we're going to do is we're going to complete the table for these examples and we're going to see what the graph looks like. So I am going to use, the log, the log, this is log base 10, the common log. I don't have to write 10, but that means the base of 10. That's a button along the left-hand side of your calculator. So the log of 0.1 is -1, so I'm going to put -1. The log of 1 is 0, and the log of 10 is 1. So if we graph that, roughly, right? Got somebody bothering me while I'm doing this. All right, so 0.1 is -1. 1 is 0. So right now we have a graph that looks like this. And if we did closer to 0, this is what we get is a vertical asymptote here at y equals 0. All right. And this thing slowly is increasing, right? If we do the same thing for the natural log, here what we were doing was 1 over 10. Here we're graphing 1 over e. So if we say the natural log of 0.368 is going to be just about -1. The natural log of 1 is 0. The natural log of 2.72 is 1. The natural log of 7.3, right, the squared, is going to be 2. So we graph this roughly. We're going to see the same shape of the graph as we see here. At 0.3, it's here. It's this. At 1, I'm sorry, 2.72, it's 1. At 7.3, 1, 2, 3, 4, 5, 6, 7, it's going to be 2. So we get the same curve. This one's a little flatter, isn't it? It's a little flatter because the base E, which is 2.72, smaller than the base up here of 10. So it's a little flatter. But it has the same general shape. So what we want to do is look at some important properties of these functions. Our domain, if we go back here, folks, what's our domain? Again, we have this vertical asymptote at y equals 0. So our domain in interval notation is 0 to infinity. Our range is always -infinity to +infinity. Remember, these log functions are inverses of the exponential. So when we had an exponential function, the domain was always all real numbers. Now that's the range of the log. In the parent exponential, the range was something like this. That's the domain of the log. End behaviors. Okay, this is what they did in the book, but let's talk about our end behaviors. As x gets really large, these things are heading to infinity, right? As x gets really small, really it ends at 0 here, these things are headed toward, as x approaches 0, these things are headed toward -infinity. That's what we see here. As x approaches infinity, f of x approaches infinity, positive. as x approaches 0 from the positive side, because it can't be on the negative side, f of x approaches negative infinity. We have a vertical, oh, I've been calling this y equals 0, gang. This is x equals 0, isn't it? We have a vertical asymptote at x equals 0. No horizontal asymptote. That's different than the exponential functions, which had a horizontal asymptote but no vertical asymptote. All right. If we look at this log function, and I'm going to do a rough look at the log function, intervals where it's increasing or decreasing, while we read a book from left to right, this graph is always increasing, isn't it? We do have an x-intercept, but we don't have any y-intercepts. Okay, so these are properties of these graphs. So similar to our exponential functions, we do have some reference points we're going to deal with. So let's write out, or let's look at the transformed function here. Notice again, we don't worry about the b, that's the horizontal stretch or shrink. Right? B means base in this case. So we will have an asymptote at x equals h, and we'll be able to transform our reference points. Okay, so let's identify for this transformed log, a equals -2. Let's see what h equals 1, k equals -2. Right? That means at x equals h, or 1 here, I have a vertical asymptote. And what does this mean? That means the whole graph was shifted 1 unit that way. K means the whole graph is shifted 2 units this way. What does this tell us, folks? It tells us that we have a reflection across the x-axis, and we have a vertical stretch, don't we? By a factor of 2. So let's do our reference points. 1 plus h is 2. K is -2. B, which in this case is 2, right? Or B is 2. B plus h is 3. And then a plus k is -4. All right, so 2 is -2. 3 is -4. So what this graph looks like is this. Right? If we go to the parent looks like this, doesn't it? So this indeed was a reflection across the x-axis. It was a vertical stretch, and it was shifted. So that makes sense, right? So we should be able to identify these things and the base of 2, get the reference points, and graph the new graph. Let's try this one. All right, so I'll write it up here. A is 2. What's the base of this function, folks? I don't see a number there. Well, that means it's the common log, and it's a base of 10. Right, h is -2. K equals 4. Okay, so we're going to graph. And we know we have an asymptote at x equals h. So x equals -2 is going to be our vertical asymptote. All right, so our first reference point is 1 plus h. 1 minus 2 is -1. And k, -1, 4. Okay, our second reference point is b plus h. 10 minus 2 is 8. A plus k is 6. So 8. 1, 2, 3, 4, 5, 6, 7, 8. And 6. 4, 5, 6. So it's something like this. There's our log function for this one. Remember, this down here, as we get really, really, really close to this asymptote, this log function is approaching negative infinity, isn't it? as the x value gets really close to that vertical asymptote. As x gets really large this way, it's approaching positive infinity. Okay. Now, here are some things we can do when we're trying to study actual sets of data. So it says you can obtain a logarithmic model two ways. You can do a logarithmic regression, okay, which we get to the same way. We hit the stat button, we go over to calc. We have number 9, looks like this, gives us a natural log regression, doesn't it? That's the one we will deal with here, a natural log regression. Or we could do an exponential regression and then find the inverse, right? Because exponentials and logs are inverses of each other. So this biologist is studying these fox populations, and he actually does an exponential regression on the data, and he finds this. Okay? Now, he's interested in a model that instead of using time as the input, it gets time as the output. So guess what? We can go and find a log function, right? Because logs are the inverse of exponentials, and when we take inverses, the inputs and outputs are swapped, aren't they? So we could do this two different ways. We could take the data right here. He used x and y for the exponential functions. We can do a logarithmic, again an ln regression, by switching x and y's. So let's come here and let's call this y and let's call this x and do an exponential regression. You'll input the data in your calculator the same way you do it for any regression, and then we'll do a number 9 log regression. So the result of my log regression looks like this: ln reg y equals a plus b times the natural log of x. So it's y equals negative 35.57 plus b 8.66 ln of x. So this is a natural log regression of this data. All right, what if we took this original function, or the exponential function he did when he got the regression, and we find its inverse using our method of finding inverses? Okay, so I'm going to try that. Okay, so if I messy like rewrote over here the function, now I need to get the exponential part by itself. So I'm going to do p over 62 equals 1.12 t. All right, let's rewrite that in the log form. All right, as I revisit this, I'm going to not worry about us finding the inverse, because that gets a little sticky and I don't want you to have to worry about it. But what you do need to understand is that based on the inputs and outputs, if we need a certain, we need the output to look like the input, we have to switch x and y in order to do these regressions. Okay, so this one we'll go through these problems as examples. But based on this, you will have a worksheet to do that will be out on PowerSchool. So give it a go and see where you have questions. Thanks.